Let us get going. So we want to finish up our discussion of wave equation in two dimensions. And here we're separating variables twice. We've got u equals a function of time v times phi, and then phi itself equals a function of h times omega. And so we already did some work, right? So by analogy with the case for one variable, when you plug in, say, v and phi into this, you end up with something like what? Negative v double prime over v equals lambda, which you can rewrite as an eigenvalue equation for v. So that equation we're quite familiar with. And you also ended up with the eigenvalue equation, or excuse me, c squared. It's on the bottom here. And you also ended up with the eigenvalue equation for the Laplacian. So you end up with something like Laplacian phi equals negative lambda times phi. And then our next step was to make this substitution phi equals h of r times omega of theta and pass to polar coordinates with our polar coordinate representation. Yeah, that whine is kind of annoying. And there's our polar form of the Laplacian. And we're assuming, of course, from the outset that we've got coordinates t, r, and theta. And so we did this, and we ended up with equations for omega and for h. So separating the variables once more ended up with a new separation constant. And so you end up with something like, what was it? Omega double prime over omega equals k squared. So the separation constant was k naught, which has to be non-negative. I think during the last lecture I said it had to be positive, but it's really just non-negative because omega doesn't have the value of 0 at 0 and 2 pi. Omega just has to have like the same value. And if you work through the argument that we did, you'll see that actually that just means that k naught has to be non-negative, not that it has to be positive. So just a small little detail there. But anyway, you still write it as k squared, where k is bigger than or equal to 0. And later on, using the periodicity of omega, we showed that in fact, k has to be an integer. So I'm just pulling this out of my mind, so if I make some typographical mistake, then be welcome to kind of correct me. But then came like the more interesting equation, which was here, this eigenvalue equation. And what was it? So we ended up with something like this. So after separating out the variables in theta and r, so we concluded this first equation we got out of this, but we also got a second equation for h. And now that second equation is what I'll write down now, with the caveat that we get lots of different solutions depending on the value of k, right? So k can be 0, 1, 2, 3, or even negative, like -1, -2, -3. And so for each one of these, you get a solution that you might call omega k. In fact, since it's a second order ODE, you get two linearly independent solutions for each k. And what do those solutions look like? Well, colloquially, I wrote it down as e to the I theta k, which is a complex solution. And I allowed K to range, from like positive values and negative values. You wouldn't so it's true that omega K can be any one of those. That's kind of fine, but I don't want you to think that this is like the general solution, like the most general solution for omega K. So let me explain what I mean. So you've got e to the I theta K equals cosine, write the constant first, K theta plus I sine K theta. And so if you've had ODE, then you're familiar with this trick that you can use to go from complex solutions to real solutions, right? You can just look at, say, since you've got a linear equation, you know that the function and its conjugate, so e to the negative I theta K, both satisfy the equation. You can divide that by 2 and you'll end up with cosine K theta. So in particular, similar argument for the imaginary part. So in particular, if you've got a complex solution to a linear equation, then the real and imaginary parts must also satisfy that equation. So for any fixed K, your general solution, so your general solution is really going to look something like AK times cosine K theta plus BK sine K theta, right? So there's some general theory from ODE that says if you've got these two independent solutions to the linear constant coefficient equation, then, or to the linear equation, then you can take all linear combinations of those solutions, and that will then give you all possible solutions. But it's nice to colloquially kind of say the possible sort of fundamental or independent solutions. Kind of they all look like e to the I theta K. But this is how to go from like this, this statement to that general solution for like real valued things. Okay, so fine, but once you've got solutions omega K, that could look something like this with constants that you choose, or could look like this if you want to choose the complex solution, then you start to realize that phi is actually going to be like hk times omega K, because now that you've got whatever solution you picked, that will then give you another solution that perhaps depends on K. So let's take, what we did is we really took omega K, was e to the I theta K last time, and we kind of plugged it back into the equation and said, okay, like what do we get now for hk? So what we got was r squared, hk double prime plus r hk prime, plus, what was it? R squared lambda minus k squared equals 0. You can check your notes and correct me if I made a mistake in recalling that. I could check my notes too, but I'm not going to. So I think that was it. Right? This was the part that was scale invariant. But maybe we had to put hk here. Yeah, and then we're good. So these were the three parts that were scale invariant, so long as lambda was 0. And that's exactly what we did. So we wanted to set about to solve this equation. And so we first started with lambda equals 0. And then we noticed that if you do some scaling, like if you take S equals R over C, then this doesn't change the form of the equation, which led to this idea that we could use what's called a homogeneous polynomial in one variable. In other words, you just look at something like R to the alpha, plug this into the equation. And that implies for you, in order for this to be 0, a condition on alpha, namely that alpha, like alpha squared minus k squared, is equal to 0, or alpha equals plus or minus k. So this led to two cases where k equals 0 gave us h0 of R equals 1, or natural log of R. So sort of your options. And again, these are your options for linearly independent solutions. The general solution would be like constant times another constant, constant plus another constant times natural log of R. But if you'll permit me, it's maybe a little bit more convenient to just kind of list off these independent solutions that we get and understand that we'll take linear combinations later. That's the problem that you get, or I mean, I don't know if it's a problem, but that's what you get when you do separation of variables. So basically, instead of taking two boundary conditions and then getting a unique solution, you take one boundary condition. We're working on the disk, radius 1. You take one boundary condition, meaning that the displacement's equal to 0 on the boundary. You do not enforce a boundary condition on the derivative, the time derivative at t equals 0. And in exchange for that, you're allowed to enforce this separation of variables. And so then your question that you ask yourself is, are those conditions interchangeable? Does the separation of variables now give you a unique solution to the equation? The answer is, of course, absolutely not. In fact, separation of variables quickly introduces these two parameters, k and lambda. And those k's and lambdas are involved in finding these linearly independent solutions for hk, omega k, which we can then take linear combinations of. And then each of those three pieces you can multiply together to get your original u. So the formula for you can write it down. I may or may not write it down in class today, but it's kind of big because it requires you kind of understanding that you can multiply like linear combinations of these independent solutions together. You get these three products that eventually give you your solution. Okay. But so now we kind of have a little bit of an embarrassment of riches. So we end up like maybe taking away some of these solutions. So in particular, we have some condition on phi, namely that phi actually has to be defined on the entire disk, and it has to be like a C2 function, like continuously differentiable. So phi is going to be something like omega k times hk. So if you look at a typical choice for omega k, like a complex, or a typical choice for phi k, excuse me, like something like, let us take k bigger than 0, but let's pick this solution r to the minus k, and let's multiply it by e to the I theta k. And if you don't want a complex solution, you could even take like one of the real or imaginary parts, because we discussed those have to solve it too. So you could look at r to the minus k times cosine theta k times a constant or something like that. And I don't intend to get like too deep into this conversation, but if you quickly ask yourself, like, is this function differentiable at r equals 0 or not? Like, what do you think? is it even continuous at r equals 0? Right, no, and what's sort of the reasoning there?
Because r to the minus k would be divided by 0?
Yeah, so the answer from the class was that you've got this 1 over r to the k, and that's blowing up near 0. Of course, it's not defined at 0. So this is not like a suitable choice for a function defined on the entire disk. Why are you getting these solutions in the first place? Well, like remember, polar coordinates aren't defined at 0 anyway. So the best polar coordinates can do is actually give you things on the punctured disk. But we don't want solutions on the punctured disk. We actually want things that are going to be well-defined in C2 on the disk. And so that means we actually need to exclude r to the minus k for k bigger than 0. 1 is fine. But natural log of r, that also blows up as r goes to 0. So I want to exclude those as well. So in fact, like among these are C2 choices. So we should exclude solutions that blow up r equals 0, and so we're left with kind of like phi k is something like r to the absolute value of k times e to the I theta k. And now this works even if k is equal to 0, because it just kind of naturally excludes natural log of r. You're left with constant function 1. And remembering in your mind, this is like a typical choice for a linearly independent solution, but this is like me telling you that there's kind of 2 independent real valued solutions there, the real and imaginary part of that complex function. So r to the absolute value of k sine k theta, and r to the absolute value of k cosine k theta. Okay, now what if lambda is bigger than 0? And so in this case, like you have to return to this equation, which is no longer scale invariant and therefore should not have an easy solution like that. So this is a nonlinear second order ODE. As far as I know, it's not solvable in elementary terms. But through a simple change of variable, you can convert this into Bessel's equation, which has a series solution. It also has an integral form. It's an equation that's well studied. I guess it first came up in astronomy, like it comes up in a lot of cases. So if lambda is bigger than 0, let's make the substitution that S equals root lambda times R. And so let's call, like before, capital HK of S to be little hk of R. And so if you don't like that, if you want an official definition is this, right? Because R is S over root lambda. And so we spent an outsized amount of time playing with these substitutions in the last class. So here I won't go over the whole, the whole rigmarole, but we'll skip to the end. So what happens when you do that change of variable? So this part stays the same. It's invariant as we talked about. So you get S squared HK double prime plus S HK prime plus, well, you can just check R squared lambda is now S squared and minus K squared HK equals 0. And so your solution will be a function of S, which you can easily convert back to R. And so this is the Bessel equation. And so it enjoys a pair of linearly independent solutions. parameterized by this integer k. Actually, k could even be a complex number, so it's solved more generally. But in our case, we're looking at integer values of k. And so the solutions are called jk and yk. There's one for each k. And I wrote down the formula for this. This is like s over 2 to the k times the sum. L goes from 0 to infinity. And then what? On the bottom, you get L factorial. You get something like the gamma function of L plus k plus 1. And on top, you get like negative s squared over 2 to the power of L. So not super interesting to you, and like you're not going to necessarily look at that and gain lots of geometric information. It does sort of, like there's graphs online, there's graphs in your book, there's lots and lots of information about this function. It does have zeros, like it's not periodic, but it does have an infinite number of positive zeros that starts at a number bigger than 0 and then increase. And going back to whether or not this times cosine theta can give you something that's differentiable, you kind of want to look at this picture here. So this term, if you look at any range of values where s is bounded, so like s goes from like 0 to root lambda. So for any positive constant lambda, you've got s has to land in that range, and so this thing you can prove will converge, uniformly converge. We'll do like a series test from calculus 2, and so you get some inequality like this is less than or equal to constant times s to the k over 2 to the k. But then s to the k, that's, as long as k is bigger than 0, s to the k just goes to 0. As r goes to 0, and gives you a nice C2 even real analytic function. If k is less than 0, or if you look at like negative k, if you look at negative k for k positive, you might say maybe that blows up, but actually you can prove that this is something like negative 1 to the k times jk of s. I don't know if I got that constant right. Let me check it. Yeah, I think I got it right. So you can prove this little relationship. It's not easy to see from there. It's easy to see from the integral representation. You can also express this as an integral. It just comes from like solving the equation from two different ways. Like if you wanted to get this series solution, what you do is you kind of literally plug in a power series with undetermined coefficients like into this equation. Just see if you can use that to determine what these coefficients have to be. It's about 5-10 pages of work online that explains that. Oh, and by the way, this gamma function, let me tell you what that is in case you've never seen it before. So if you look at gamma function of, so I'll just write down the definition. So this is like integral from 0 to infinity. And I should look it up just to make sure I don't write down the wrong thing. So take x to the z minus 1 and multiply by e to the minus x dx. And so this is like a generalization of the factorial function, valid for all complex arguments here. But if z was like equal to a natural number. So if z is like n plus 1, then you can prove that gamma of n plus 1 is like n factorial. I think in your textbook, they actually write a factorial there instead of the gamma function, but that'll be confusing to you if you ever have to look at negative k. And, you know, if you took ODE with me whenever, then we also discussed that a little bit in that class too. So basically what I'm saying is this is a factorial unless k is negative, and then the first few factors are that gamma. And to my mind, that's why it's not so easy to see this relationship from that formula, although maybe I could work it out with some time. But the upshot is this is the solution, and it is C2. This one I don't want to talk about because like in some of these other cases, this is the independent solution that blows up at r equals 0. So since we're going to exclude it anyway, I won't talk about it. Okay. And this tells us, but you can look it up. These are Bessel functions of the first kind. And well, just the Wikipedia page on Bessel functions actually has all this information. I forget which kind that is, but this notation of JK and YK is pretty standard. So now to sum up, like what we learned, in lambda bigger than 0, we get something like phi k looks like e to the I k theta times jk of s, but s is root lambda times r. So now these functions have a quite different character for positive lambda as opposed to lambda equals 0. Now in case lambda is negative, like very similar argument. For lambda less than 0, just, you know, take negative lambda. That's now positive. Take its square root, s equals root lambda. And just percolate through. And then when you get to this equation, the only difference now is that s squared is negative lambda r squared. So you get this minus sign, which you can change to like minus s plus k. And this modification of the Bessel equation is called, you guessed it, the modified Bessel equation. And yeah, it's also well studied, and it's got power series solution. It's got power series solutions. They're called IK. And then K was subscript K. And this one again is going to blow up as R goes to 0, so I won't talk about it. This one is very similar to JK. So here's its formula. You just take away this minus sign, and then you're good. So that modification to the Bessel equation sort of did that modification to the solution. And there's a little formula that relates I and J. I wrote it down, I'll just tell you. So IK of S is equal to I to the minus K JK of I times S, where I is the square root of -1. And it's not obvious from this, but if S is a positive number, then these will both be real valued. And in fact, this will be the formula. But that's like a little relationship that always holds good. Or if this is a concrete formula that's true and correct. Okay. So like maybe it's good to look at, I'll call them like fundamental choices for phi k. We'll kind of like organize them in a list. So if lambda was positive, then you get phi k, so e to the I, a theta, jk root lambda times r, lambda equals 0, e to the ik theta times r to the absolute value of k, lambda less than 0, you get e to the ik theta times now ik of root minus lambda times r, just making that substitution for s. And again, yes, these are complex valued solutions. If you wanted to turn this into like a pair of fundamental solutions for each k, or linearly independent solutions for each k, then you know how to do that. So like the general solution, well, I'll stop saying general solution because now phi k solves the eigenvalue equation that I just erased. These individual things came from independent solutions to the associated ODE that we got. But certainly, since the eigenvalue equation is still linear, like you can take the real part of these, the imaginary part of these, they'll still be solutions. You can add them together to create like real valued solutions. So you could choose phi k equals like sine k theta times jk root lambda r, or a sine theta plus, or a cosine theta plus b sine theta. A cosine k theta plus b sine k theta, times jk root lambda r starts to become a mouthful. But so you're just remembering that you have lots of options for phi k, and then you can add like phi k and phi l together, right? You can keep adding them together, and it'll still solve the eigenvalue problem by linearity. It's just that we're organizing these fundamental frequencies like according to the values of k. Yeah, question? Say it again?
PL? Is that what you just said?
Yeah, phi L. So like, I'm just saying like if you, like phi k definitely solves this equation, right? It solves minus lambda phi k. But I'm just saying like, I don't want you to think that that is the solution of that equation, because like this also solves it. It's by linearity, right?
Oh, it's just another version.
Right. So you just pick a different integer and add them together. And again, if you like real value solutions, you could do something like cosine k theta times that plus sine of L theta. Like you're just sort of like adding up the different vibrational frequencies. And we'll get to that. So now we actually do want to talk about some harmonics a little bit. I'll fill in just one tiny detail first. So I guess I erased it now, but we had this equation that was like v double prime equals c squared minus c squared lambda v. And we get that from the initial separation of variables from this step. Which means that in an analogous manner to omega, we now have that v should look something like e to the c root lambda times t times I. I mean, just skipping the whole thing of going through the characteristic polynomial and taking the roots and then writing them out, and because we did it for a w, but just with a different. With w, it was just minus lambda, so here comes like c squared on that. And the point being that just like before, these are the frequencies, so it's c times root lambda. So determining lambda with more specificity now determines for us the frequencies. So here is where we bring in the boundary condition on the drumhead, namely that u of t1 theta should equal to 0, so your displacement is being held steady, held to 0 on the boundary. And when you go look at your factorization, so this is telling you that hk of r, or excuse me, hk of root lambda times 1 equals 0. So we have to have this condition on our function hk. So you kind of go through the list. So first let's handle what if lambda were equal to 0. And so then hk is actually getting myself messed up here. So hk of 1. When I substitute in hk for jk, then I'll have this composition, but I don't have that composition here. So here hk is just r to the absolute value of k. And plugging in 1, you're not going to get any zeros. So no solution of this form satisfies the boundary values for the drum. So you can kind of exclude it. Same thing here with this version of hk, plugging in 1 for r and setting it equal to 0. You look at the graphs of the IKs, they all kind of look like that. So, I mean, there's maybe a 0 right down at 0, but certainly not at r equals 1. There's no zeros. So you have to exclude both these possibilities. So in fact, these possibilities are not excluded by the eigenvalue equation, but they are excluded by the so-called Dirichlet boundary conditions, by the condition of specifying that the boundary displacement is equal to 0. So you're left with this setup, and so now hk has to be 0, so you're left with this Bessel function, root lambda, has to be equal to 0. And so there are an infinite number of zeros for each k. That's true, that's fine. There's a chart where like the first 4 or 5 of them are approximated in your textbook. You can also like look at the graph on Desmos or whatever your favorite graphing software is, and you can kind of see that they exist. I'll take it for granted in this case that we do have like a sequence of zeros given, you know, you could call them like lowercase j, k. You start the first one at 1, I think. try to keep notationally consistent. K starts at 0, and then this start the first 0 at 1. And so that is telling you that actually you've got kind of like an itemized list, a doubly indexed sequence of possible lambdas. And just squaring both sides. Here's your eigenvalue. It's the ith 0 of jk, and then square it, and therefore your frequency. Your frequencies are going to be looking something like propagation speeds times jki squared. And so I want to kind of look at this fundamental frequency. So I want to take k equals 0 and I equals 1. And what's kind of this pure tone solution that corresponds with that? So I need u of tr theta equals v times h0 times omega 0, and we're here in this first category. So in this case, e to the I0 is 1, and I get the J0. And V is just V. So it's like e to the IT, but with lambda replaced by what it is. And actually, I'll write out the real valued solution. So I'll take like some constant times cosine of C, and this is be like J0, 1 times T plus some constant times sine of C, J0, 1 times T multiplied by this Bessel function, J01 R. Ran a little bit out of the board there. And you can actually see videos of this. So there's a nice image on Wikipedia that you can look at. Bill has actually found some YouTube videos that show a real, vibrating drum head. They're using the frequencies to vibrate the head so that you can like see the patterns, and I'll put that online. So thanks for finding those and sharing them. I don't really have time to kind of like set it all up to display it on the board right now, but when you're looking, they're all organized by frequencies, right? So when you're looking at the fundamental frequency, where it's just kind of drum head, then that's your equation that's governing it. Yeah.
Little j sub k1 per ki, those are just the zeros of what? Of the j function?
Yeah, so there's an infinite sequence of Bessel functions that solve the equation, J0, J1, J2, J3, J4, and each one of those functions now has an infinite number of positive zeros. So lowercase jki is the ith 0 taken in increasing order of the Bessel function jk. The question was, please explain the terminology here one more time. Cool. I won't write anything else down because we're starting to get over, but I'll just say, if you look at these like pure tone solutions, they can solve like this problem where you've got your boundary value equal to 0, but the time derivative of the function is determined for you. Like, what if you wanted to go the other way? What if you wanted to say, I want to prescribe this being 0, or even something else, and I want to also prescribe the time derivative at 0 to be some function h. So, like, is it possible to write this as a sum of these vibrational frequency solutions? So in other words, this is the question that Fourier asked. So can I take this solution and take the corresponding one for k equals 1 and add them together, take the corresponding one for k equals 2, add them together, just continue down an infinite list. And so now I've got A0, B0, A1, B1, A2, B2. I get to choose this infinite sequence of coefficients. Can I make choices of those coefficients to give me any boundary values that I want? So that's the question, to connect physics and mathematics, to connect individual vibrational frequencies to being able to solve the PDE for any boundary values. The question of whether or not you can take a general function and write it as a linear combination of these cosines and sines of varying frequencies. So that's called Fourier, Fourier analysis, or like the beginning of Fourier analysis. And so that's the question we'll take up on Monday.